Hello everyone. So this is our officially first class, but you can say the second class or second video for basics of organic chemistry. And in the previous video, I had told the very basic introduction about organic chemistry and how we can classify chemistry into three different parts: physical chemistry, organic chemistry, and inorganic chemistry, and what is the difference between all of these three, right? Along with that, we had also understood why carbon is a very important element and very important part of organic chemistry, why all the organic compounds have one basic skeleton made up of carbon, and what makes carbon so special, why it is so versatile in nature. So after knowing all this, we had understood the basics of from where to obtain organic compounds, what all different type of elements can engage themselves to form organic compound, why carbon and hydrogen are very important part of organic compound, essentially carbon making the main backbone of organic compounds. We can also call our organic compounds as hydrocarbons, but hydrocarbons is a little simple version in which you have the chains made up of only carbon and hydrogen. Whereas when we talk about organic compounds consist of the compounds made up of carbon, hydrogen, and may have some other elements also like oxygen, chlorine, bromine, iodine in lesser proportion. Today, we will understand how to classify organic compounds and why it is important. First of all, we need to understand why classification is important. Classification is important because we have millions and trillions of organic compounds. Every living and dead organic matter is made up of organic compounds. We just cannot study about their properties like physical properties, chemical properties, appearances for so many compounds. So what we do to simplify our learning, we basically categorize the compounds in different categories. The ones which have similar properties, similar chemical properties, we categorize them into specific categories so that it becomes easier to study them. Secondly, those millions and trillions compounds shrink down into smaller lists so that you just remember, you just talk about a specific name or classification or a list, and that will show up or that will explain you majority of the properties of the compounds in that list. So basically simplifying the properties, simplifying the way of learning about so many organic compounds is the reason for the classification. Forget about properties. Even naming so many compounds randomly is very difficult. So if we classify them into smaller categories, naming, applying the rules, applying the specific rules on those categories becomes easier, and you don't have to mug or cram up a lot. You just know the concept behind each and every category and you will get it. So classification is nothing but to simplify the learning process of different organic compounds. Okay. So in grade 10th also we have learned some classifications where we have learned organic compounds can be divided into two main categories. One is saturated compounds and another is unsaturated compounds. And at that time we had understood that the classification we have done on the basis of type of bonds exist between carbon and carbon, but that cannot be the only basis for the classification. There are many more ways to classify, and there are many more categories of class of there are many more categories of organic compounds. So in grade 11th, we will be dealing with a good chunk of such compounds and the classifications and subcategories and so on. So we will be dealing with many different compounds, with the simple chains, with the complex chains, with the cyclic chains, with the functional groups. We will be dealing with everything one by one in detail, slowly, and in the very explained manner. Let's see the table of classification first. So if we talk about the organic compounds can be classified into two major categories. One is open chain compounds and another is closed chain compounds. I'll be explaining you all the terminologies in detail, in short. Even though you know it or you don't know it, it's good to have a knowledge about everything so that later on you do not suffer with the problem that I don't know what this term means. So open chain means where your chain has two different ends, basically starting end and the starting end and the terminating end. Now when I'm talking about the starting end and the terminating end, if I look at the compound like this: CH3, CH2, 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 CH3. So it has two ends. Assume this is the starting end, this is going to be terminating end. So these kind of chains are called as open chains, which are like chains. All of you know what are chains, which have two ends. Okay, so open chain compounds are also called as acyclic compounds. All these terms are mandatory to know, because when the question will be asked, they can use any term and you should be able to interpret it, you should be able to understand what they are talking about. So open chain, which have two separate ends, one starting end and another is terminating end. These compounds are also called as aliphatic compounds. Aliphatic compounds, acyclic compounds, open chain compounds belong to the same thing. They are just synonyms of the same compound or same type of compounds. Now these open chain compounds can further divided into two categories, which we have learned in grade 10, and that is saturated and unsaturated compounds. All of us know saturated and unsaturated division has been made on the basis of what kind of bonding your carbon-carbon possess, or the pair of carbon possess. If in the chain all the carbons are linked through the single bond, the compounds are called as saturated carbons, and we can further specify it by the name alkanes. Unsaturated are the ones where in the chain you will find at least one pair of carbon carrying multiple bonds. What kind of multiple bonds? It can have carbon double bond carbon, it can have carbon triple bond carbon. So these bonds are called as multiple bonds. As I mentioned, it can be any number of double bonds and triple bonds in the chain, but the minimum number is one double bond and one triple bond in the chain, along with the combination of carbon single bond carbon in rest of the chain. For example, if I say I have CH3, CH2, CH2, CH double bond CH2. So in this chain, I have 1, 2, 3, 4, 5 carbons, out of which 4 carbons are linked with each other through the single bond, whereas fourth and fifth carbon is linked with each other using the double bond. So there is one multiple bond. So minimum presence of one multiple bond is required. You can have you can have different number of multiple bonds also. Okay. So these are called as double bonded compounds are called as alkenes, and triple bonded compounds are called as alkynes. As simple as that. We have learned a lot of details about it in grade 10, how to name them, how these look like, how the bonding happens in these compounds. But still, I'll be revising everything so that you do not lose that connect, or you can come into the continuous mode of understanding rather than recalling what was done in grade 10. So we will be dealing with each and every group irrespective of you have done it in grade 10th. We will still be doing it, and we'll be doing it from the scratch to make the understanding much better and easier. Next type of compounds which you have not studied in grade 10 are closed chain compounds. Closed chain compounds means where there are no ends. Basically, all the carbons have been linked in such a way that chain becomes cyclic. It becomes a closed chain and it doesn't have any end. For example, if you talk about circle, you talk about square. It doesn't these things don't have any ends. Similarly, if I connect my carbon like this, CH2 single bond CH2 single bond CH2 single bond CH2. So we can see there is no starting end and no terminating end. Such kind of compounds are called as closed chain compounds. Now there are many ways how we can draw them. There are many different compounds. Here I have drawn an example where we have all single bonds, but we can have, and we will see the compounds having double bond also, having triple bond also in the closed chain, having the functional groups also, and many a times you will have the closed chains where it is not made up of all carbons, but the actual skeleton is made by carbon and some other elements also. For example, if I draw the compound like this, CH, give me a moment. So if I draw the compound like CH2, 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 and NH. I think my drawing is a little poor. So this is what we have made as a closed chain, and here what we have done is the chain is made up of 5 carbons and 1 nitrogen. nitrogen with one hydrogen. So basically, the chain is not only made up of carbon but is also made up of nitrogen. Actual chain itself has the skeleton made up of carbon and nitrogen. So we will see such kind of compounds very often, and we will also learn how to name these compounds, how to identify these compounds, and how to put them into a certain category. Okay, so closed chain compounds are also called as cyclic compounds. Opposite to the open chains are called as acyclic, and these are called as cyclic. So this is just simple opposite of acyclic. These acyclic compounds are further classified into homocyclic compounds and heterocyclic compounds. Now here these terms you have to understand. We will be dealing with a lot of examples of such categories, but for now, in short, let's have an idea. Homocyclic compounds. Homocyclic compounds, as the name suggests, homo means similarity or similar. So basically when the cycle is made up of, or whole compound is made up of same type of element only, then the compound will be known as homocyclic compound. When we are talking about the organic compound, we are expecting the compound to be made up of carbon. So when I am saying homocyclic compound, we are expecting the compound to be made up of only carbon. It cannot be only nitrogen, it cannot be only oxygen, because those will not be considered as organic compounds. So the only possible compound is the compounds which are made up of the one single element as in the main chain, and that is carbon, and carbon valencies are fulfilled further using hydrogen or some other elements, but the main skeleton of the compound is made up of carbon. So the compound like this, if you can see, it's made up of only carbon, 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 and carbon valencies are fulfilled later on by hydrogen. These valencies can be fulfilled by some other element also, but actual compound or actual skeleton should be made up of only carbon. For example, let me just show you. If I draw CH2, 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 or I should not write in this way because that may lead to the confusion. So I'll just write the actual skeleton. Actual skeleton is like this. And now we will fill the valencies of the carbon. So this is carbon 1 with 2 valencies unsatisfied. Let's put H2 over here. Again, this carbon 2 has 2 valencies fulfilled, 2 unfulfilled. Let's write CH2. Okay, ignore this 2. This is the third carbon. Again, 2 valencies are fulfilled. And let's write 2 here to fill the tetravalency. This kind of compound will be called as homocyclic. In fact, let me just show you one more thing. If I alter it in some manner, like I make the skeleton made up of carbon only, and now to fulfill the valency, rather than using hydrogen, if I have used any other element also, still it will be called as homocyclic compound because the actual cycle is made up of carbon only. For example, if I fulfill the valencies of carbon using chlorine, here I have used hydrogen, here I have used hydrogen, but for one carbon I have used chlorine. It still be called as homocyclic compound because your actual chain is made up of only carbons. Okay. Next comes to the heterocyclic compound. Heterocyclic compound, as I have shown you one example over here. Let me just rewrite it. My skeleton is made up of carbon and some other element. Let's write oxygen now to just give you a different example. One I have already mentioned over here. So here, now I'll try to fulfill the valency. So it will be hydrogen, hydrogen over here. Let's say write H2, 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 and oxygen valency is already fulfilled. So such kind of compound which is made up of carbon and an extra element, that is oxygen. So actual skeleton of the cyclic structure is made up of carbon and oxygen. Such compounds are called as heterocyclic compounds. So this is my heterocyclic compound. Now come to the next part. Next part is homocyclic compounds can be further divided into alicyclic compounds and aromatic compounds. Let me just explain you what is alicyclic compound and aromatic compounds. So, alicyclic compounds are the simple cyclic structures which are homocyclic and do not possess any specific property or any different kind of property or any different appearance they have. Basically, you cannot judge it just by looking at it. If you know what are aromatic compounds, you will be able to understand if a compound is not aromatic, then it is simply alicyclic compound. So first, let's understand what is aromatic compound. We cannot understand it in much more details, but still I can give you a slight idea about it. We will be talking about it in lot detail going forward. So, aromatic compounds are compounds which have a specific arrangement, to be honest, and that arrangement is like benzene or benzene-based structures are called as aromatic compounds, or you can say there are few compounds which you will find having 4n plus 2 pi electrons. Any compound containing 4n plus 2 pi electrons are generally considered as aromatic compounds. What do you mean by 4n plus 2 pi electrons? N is any whole number starting from 1. Here you will find there will be multiple pi bonds in a cyclic structure, and those pi bonds will be on the alternate positions to each other. Though that's not the only definition, but that's a simple definition to be explained. We will be talking about aromatic compounds soon. Let's say if I draw a structure like CH, CH. Okay, let me just write it over here. C, 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 and this. And I form pi bonds on the alternate positions. And then I fulfill the valency with the hydrogen. This compound is called as benzene. The most commonly known and most widely used aromatic compound. Now, if you see how many pi electrons it has, each pi bond consists 2 pi electrons. So 2 electrons here, 2 electrons here, and 2 electrons here. So total 6 electrons, 6 pi electrons this particular compound contains. Does it follow this 4n plus 2 pi electrons rule? Yes, it does, where n is equal to 1. If n is equal to 1, then it will give you the value of this thing as 6. So 6 pi electrons this particular compound has, and this is the basic you can say term to explain, or this is the basic condition to know whether a compound is aromatic or not. What do you mean by aromatic? How these compounds are different from the normal compounds? We will talk about it in detail. They tend to show a specific property which is called as resonance. What is resonance? How it looks like, how it makes a difference in a compound, all this we'll be talking about. I don't want to rush it up, and we are going to do these particular topics in a lot more detail. Hence, let's not get indulge into the details of it. We'll just get a slight idea about these things so that we can start the chapter, and then one by one we'll come to each category and we'll get a detailed understanding. Okay, so compounds which generally have 4n plus 2 pi electrons, and those pi bonds are alternatively distributed in the compound are come under the category of organic compounds. One important example for it is benzene. Now you can say not only benzene is the compound which can be aromatic, or not only benzene based compounds can be aromatic. There are compounds which are not benzene or not benzene like but still are aromatic, and let me give you an example for that. So I have drawn a structure over here, and this is called as cyclopent or cyclopent 1,4 diene cation, sorry, anion. What we can see in this structure is we have 2 pi bonds and a negative charge on a carbon. This is a species which gets formed when the reaction takes place. Okay, and how it is forming, when it is forming, we will deal with it later on, but this is just an example to show how without looking like benzene or without being benzene, how a compound can be aromatic. Okay, very in the very simpler terms, I'm giving you some examples. You may or may not be able to follow them up. Wait for it, have the patience. We will come to these topics again and we'll talk about them in much more detail. Now, as I mentioned that aromatic compounds have to have 4n plus 2 pi electrons. If they have these many electrons and the double bonds or these pi electrons are on the alternate position, then they satisfy the condition of being aromatic. Okay, and let's see whether this condition gets satisfied here or not. So we have one pi bond over here, so that means two electrons here, two electrons here, and mind it, negative charge also acts as pi electrons. The charge, negative charge which has formed due to the excess electron, those two electrons which are causing the formation of the negative charge are also called as pi electrons. Why, how, we will look at the structures later on. But for now, take it as a fact that the negative charge is because of these two electrons. One electron is the carbon's own electron, and one electron is of some species which has broken its bond with the carbon and given away the electron. So the negative charge is 1, and you can see two lone electrons over, two lone pair of electrons. So these two lone pair of electrons are also called as pi electrons, even if this two lone pair of electrons are not mentioned over here, you still have to consider, or you have to have that simple understanding that negative charge is due to not one electron is carbon's own electron, and the another electron has to be the electron taken away from the species which was originally present over there. Let me show an example to you. If, let's say, my compound was like this was my compound, and we had hydrogen over here. Okay, this is the carbon. All of us have learned periodic properties. All of us know the electronegativity and electropositivity of the elements. We know that hydrogen is an electropositive element and carbon is an electronegative element. So when carbon has to break the bond with hydrogen, hydrogen will give away its electron to carbon, like the same way how when the HCl bond breaks, what happens? It comes out as H plus and Cl minus. So when you talk about Cl minus, Cl already has 7 electrons of its own, and it gets one from hydrogen, and that's how it gets a negative charge, right? So exactly same thing is happening over here. Assume the bond is broken between carbon and hydrogen, and it has been broken in such a way that hydrogen comes out as H plus. So what this carbon will be left with? The carbon will be left with one of its own electron and one electron which it has taken from hydrogen, or basically it has pulled the whole shared pair of electron towards itself, leaving the hydrogen with no electron. Basically, there was a bond between carbon and hydrogen which was made up of two electrons. It has pulled both of them towards itself, out of which one electron was its own, another electron is hydrogen's, and that extra electron is causing the formation of negative charge on that carbon. So do not get confused by the presence of two electrons over here. Out of these two, one is normally the carbon's electron, and one electron is the one which it has snatched from the other species which was present with the carbon. So this pair of electron is also called as pi electron, or pi, this lone pair is also called as pi electrons. So that means I will consider these electrons also for my calculation. So two electrons here, two electrons here, two electrons here, so total 6 electrons, and hence it satisfies the condition of 4n plus 2 pi. So 4n plus 2 pi electrons present in this compound, which looks like this. And it doesn't look like benzene. It is not a benzene derivative. What is benzene derivative? Benzene derivative means benzene based compounds. That means if I draw the compound like this is benzene derivative. That means here you have benzene and then there is an extra attachment over here. But that is not the case over here. This compound is entirely different from benzene, and hence it comes under the category of non-benzenoid compounds, and benzene or benzene based compounds are called as benzenoid aromatic compounds. So benzenoid, as the name suggests, is benzene based, and non-benzenoid, as the name suggests, means the ones which are based on, or which are not made up of benzene but have the aromatic character. Now, why I had explained you the aromatic compounds first, because they possess a specific property or specific quality or specific kind of behavior they exhibit. Any compound which does not come under this category will be considered as alicyclic compounds. For example, If I talk about this compound, which can also be written as CH2, sorry, my bad, which can also be written as CH, CH, CH2, CH2, and a double bond over here. So this does not follow any aromatic rule over here, and it will become considered as simple alicyclic compound. Similarly, if I draw anything like cyclohexane, so cyclohexane is nothing else but CH2, 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 and CH2, right? And this kind of compound also does not possess any aromatic type of property or aromatic type of pi electrons, and hence it will be considered as alicyclic compound. So any compound which is not aromatic comes under the category of alicyclic compounds only and only if it is homocyclic. Okay, so basically the actual category is alicyclic homocyclic compounds, because the same category is there in heterocyclic compounds also. Again, let's talk about the heterocyclic compounds, where we have same categories, same way it is named as it was in the homocyclic compounds. So we have two categories over here, alicyclic compounds and aromatic compounds. Now again, aromatic compounds are the ones which follow 4n plus 2 pi rule. But as I mentioned, heterocyclic are the compounds where the cycle is not only made up of carbon, but may have some other element, not may, but must have some other element involved. So let me give you an example of aromatic compound, which is heterocyclic. That means the chain is not made up of only carbon. So let's see on the board over here. Okay, so I have drawn a compound over here, and this compound is CH, single bond CH, double bond CH, double bond CH, single bond NH, where N has a lone pair. Okay, and we have how many pi electrons over here? One pi bond is here. So two electrons from here, two electrons from here, and two electrons are from this lone pair. These two lone pair electrons are also considered as pi electrons. Why? How? We will understand everything. For now, just try to understand whatever maximum you can. We will be talking about all the rules, how the structure looks like, how this lone pair is being considered as pi electron. We will be dealing with all that slowly. Have patience, have the understanding. Even if you're able to understand 20% of it, that will help you in understanding the rest of the chapter. Okay, so I just take it as a matter of fact that this pair of electron is also being considered as pi electrons, and hence we have total 6 pi electrons, which again follows the rule of 4n plus 2 pi. And because it has this nitrogen which is making the actual backbone of the molecule, this is called as heterocyclic aromatic compound. What are alicyclic compounds? Heterocyclic alicyclic compounds, the ones which do not follow the aromatic rules, will be considered as heterocyclic alicyclic compounds. We will be talking about these all categories with examples very soon. So wait for it. We will be dealing with them. We will be doing a lot of examples, and I'll make sure that there will be nothing which you don't know about these compounds or anything inorganic. So don't worry. Try to understand as much as possible. Organic chemistry is the thing where the understanding builds up slowly. It's like linking the small things, and because it is lot conceptual and the concept builds up slowly, it takes its own sweet time to know the concept. Before knowing the concept, you need to be aware of some terminology. So right now we are in the phase where we are trying to understand some terms. Once we know the terms, the scientific terms which are required to deal with organic chemistry, we will come up to the logical part, and then the things will be much more easier for you to understand. Okay, so this is the classification of organic compounds. Let's talk about the next part, where I'm eventually going to deal with each and every type of compound. What is their name? Or, I mean, all these categories basically, what are their names, how to represent them, what are their suffixes and prefixes, how their common names work, and how their IUPAC name works. So here, let's quickly talk about the small, before I go to the details of each and every type of compound. Here I have listed down some examples, a single example, but I'll give you many more examples for each category. Here is just a small list to make you understand whatever we have done just now, or to quickly revise whatever we have done. So alkanes, as I mentioned, are the saturated compounds, have the single bonds only, and I have taken an example over here, CH3, CH2, CH3. This is called as propane. Alkenes are the ones which are unsaturated hydrocarbons and must have at least one double bond structure or carbon double bond carbon combination. Example, I have taken CH3, CH double bond CH2, and it is called as propene. Similarly, we have alkynes, which are the triple bonded structures. So CH triple bond CH I have taken, this is ethane. Now, next type of compounds, what we can have is aliphatic compounds with functional groups. Basically, the normal straight chain compounds having functional groups in them. So I have shown it over here. You are quite aware of these compounds because you have dealt with them, at least few of them, in grade 10th. So here I have taken CH3, CH2OH. The chain is not only made up of carbon and hydrogen but has OH, an extra compound or extra element over here, which is also called as functional group. So we can have normal straight chain compounds carrying some functional groups also. Example is ethanol. Similarly, we have CH3, CH2, COOH. Both the groups I have taken, the ones which you have dealt with already in grade 10th. Okay, so this is alcohol group, this is carboxylic acid group. So we have the normal straight chain compounds with functional groups. This is ethanol and this is propanoic acid. I'm not very sure whether you remember how to name these compounds or not, but even if you don't, then don't worry, we are going to do the namings of each and every type of compound very soon. Next is homoalicyclic compounds. Homoalicyclic compounds, as I mentioned, are the ones which are cyclic structures made up of only carbon. So this is cyclohexane. All the 6 positions are made up of carbon, no other element, and the valencies are being fulfilled by hydrogen. Next is heterocyclic compound, where the actual skeleton of the compound is made up of carbon as well as some other element. Here we have used carbon and oxygen. This compound has a name cyclohexane. This compound has a name tetrahydropyrane. Though names are not very important right now because you don't know how to name them. This is IUPAC name, or this is the actual scientific name for this compound, but this is a common name. So you won't be able to figure out right now whether we are using common name or we are using the scientific names. So this is just for your information. Keep a note of it because we will be using these names later on. But mind it, you don't have to mug it up right now. There will be some places where most of them you'll be able to understand and you'll be able to write on your own. The common names are definitely the ones which don't have any logic but just simple names given by some scientists. So those you will have to mug up, but the scientific names, which are also called as IUPAC names, will be explained in detail, and there you won't have to remember everything. You will just look at the structure and you will be able to name it on your own. Next is heterocyclic aromatic compound. Aromatic, I have told you, the ones which have 4n plus 2 pi electrons present in them, and those pi electrons must be on the alternate positions. Let me just show you. So here, this is the structure. Here the compound is made up of carbon and nitrogen, and here we have one pi bond over here, one pi bond over here, and one pi bond over here, and a lone pair over here. By the way, in this case, though it can be a little confusing part for you because you will wonder why in the previous example nitrogen's lone pair was taken as pi electron but not in this case, and your question is absolutely valid. And as I mentioned, it is too early to understand these things, and it requires a lot of other basic knowledge. So wait for it and we will understand. Right now, this nitrogen's lone pair is not is not being considered in pi electrons. Why? Because why we will understand it later, but I can give you a small hint. Look at the pi bonds position and the pi electron position. This is my pi bonds. These are on the alternate positions, and this pi electron is not on the alternate position and hence will not be considered. I told you the pi electrons, the pi bonds which are on the alternate position are the ones which we are going to consider. The ones which are not on the alternate positions, we are not going to consider. Okay, so because this pi bond and these lone pairs are immediately after each other, we can just take only one pair of pi electrons into the consideration and other we have to ignore. So we are ignoring this lone pair and we are taking this pi bonds electrons as the actual ones in calculation. So we have three pi electron pairs in consideration, one here, one here, one here, and the lone pair has got ignored. Why? Because it was not on the alternate position. So we again have 4n plus 2 pi rule following. We again have 4n plus 2 pi electrons present, and hence this is aromatic and heterocyclic also. Similarly, we have homocyclic benzenoid aromatic compounds. I told you benzenoid are the ones where the compounds are made up of benzene, or benzene itself will come under the category of homocyclic benzenoid aromatic compounds. So benzene with OH, or two benzenes attached to each other, all these will be considered as homocyclic benzenoid aromatic compounds. This compound is called as phenol. These two benzene chains attached to each other are called as naphthalene, and we will talk about it in detail again, so do not get confused. This is just some terminologies what we are understanding here. I'm not explaining you any logic here. We are not understanding any concept. These are just some terms which you should know, so that whenever I'll use it later on, you will be able to relate what I'm talking about. Next is homocyclic non-benzenoid aromatic compound. So basically the one which is not benzene but homocyclic. So this compound, if you look at it, has 18 carbons. It totally doesn't look like benzene. Benzene is made up of 6 carbons. All the double bonds are on the alternate position and definitely follow the 4n plus 2 pi electron rule. Okay, and this compound is called as 18-enulene. How, why, that also we'll talk about. But this is one of the most complicated example or structure of homocyclic non-benzenoid aromatic compound. We can have the simple ones also, but okay, we are good with it. Okay, so this is the revision of what we have done just now in classification. A quick revision, a quick brief, and we will be dealing with a lot more other examples for these compounds.